Hi guys, we are now in module 2. Before we discuss gases and equation of state, now we will look at the bigger picture by discussing the first law of thermodynamics, including applications in ideal gas processes as well as thermochemistry. After studying this module, you should be able to accomplish the following outcomes. First is to state and define equations and characteristics of heat capacity, and work. Differentiate reversible and irreversible conditions. Define internal energy. And state and apply the first law of thermodynamics occurring at different conditions. Isothermal, isobaric, adiabatic, reversible, and irreversible changes. Now, when we say thermodynamics, this involves study of energy and its transformations. Thermo is related with energy, and dynamics is related with transformations. Thermodynamics is also the study of the restrictions on the possible properties of matter or unpermissible physical processes. It tries to establish relationship between states of matter like pressure, temperature, volume, internal energy, enthalpy, and entropy. But before we discuss the first law of thermodynamics, let us first review some thermodynamic definitions. First is system. When we say system, this is the object or region or part of the universe in which we have special interest. And everything else or outside the system, we call it surroundings. Due to vastness of the universe, the conditions of temperature and pressure remain constant. And system and surroundings is separated by a wall or a barrier that separates the two. So the definition of the system is very dependent upon the boundaries which separate the system and surroundings. So boundary may be actual or notional and controls transfer of work, heat, and matter from system and surroundings. Now, we have different types of system. When we say open system, matter can go in and out of the system. This provides exchange between matter and energy. However, for closed system, there is an exchange of energy but not in mass. So matter cannot go in and out of the system. The boundary doesn't allow mass transfer. But if the boundary does not allow heat flow, the system is called adiabatic. And if the boundary doesn't allow both mass transfer as well as heat flow, the system is called isolated. So if we will give example of the three types of system, so example, you have a test tube with your solution that you are observing. So if you have an open test tube, this is considered as an open system. There is an exchange between mass and heat. However, if you close the test tube, this could be considered in a closed system. And if the test tube is under the insulated wall, we call it isolated system. Now, another terms that we will be discussing in detail when we study the first law of thermodynamics are energy, work, and heat. So you know that energy, by definition, this is the capacity to do work or ability to do work. The energy of the system can be changed into work and heat, and the SI unit is called joule, or for molar energy, we call it kilojoule per mole. Now, what about work? Work is a form of energy which can transfer in and out of the system that is stored in the organized motion of molecules. Work is done when an object is moved against some opposing force. So displacement is an important factor here. And lastly, we have heat as a form of energy, which can also be transferred in and out of the system that is stored in a random motion of molecules. If the energy difference of a system results from a temperature difference between it and the surroundings, energy has been transferred as heat. So take note that for heat energy transfer, there is random molecular motion. While for work energy transfer, this is considered uniform molecular motion. Now, work here is a method of energy transfer. Work is energy which is being transferred across the boundary of the thermodynamic system during a change in its state and which could be converted completely into a lifting of weight in the surroundings. Now, take note of the sign conventions for work. Work is negative if work is done by the system on the surroundings, and work is positive if this is done on the system by the surroundings. What about heat? The sign conventions for heat, since this involves transfer of energy by means of a temperature difference between system and surroundings, if the Q of system becomes negative, if heat transferred from the system going to the surroundings, and vice versa, Q system becomes positive if heat transferred to the system from the surroundings. So to understand it better, if this is our system, so heat flow into, sign convention of heat is positive. Heat flow out, negative Q. Work done on the system, we have positive W. Example is compression of gas. And work done by the system, we have negative work. Good example is expansion of gases. So since system and surroundings are separated by a wall, so a diathermic or permeable system, so this is a system in which energy is allowed in and out in the form of heat system in contact with the surroundings. So if the boundary is impermeable, so a system which heat is not allowed in or out, we have what we call the adiabatic system that is separated by an adiabatic wall. Now, more about conventions or terms involving heat. So we have an endothermic process. If the process absorbs heat, and if the process releases heat, we have an exothermic process. Exothermic process in a diathermic container, what happens? It decreases the temperature of the surroundings. While exothermic process in the diathermic, it increases. Since this releases heat, it increases temperature of the surroundings. Now, we also need to review the difference between intensive and extensive properties. So when we say extensive, this is dependent upon the amount of matter or properties whose values are increased or decreased in direct proportion to the enlargement or reduction of the system. So what are examples of extensive properties? So examples include volume, internal energy, enthalpy, number of moles. So to understand it better, example, if we are considering volume, the total volume of, let's say, certain gas in a system is equal to the sum of its partial volumes. So while intensive property, this is independent of the amount of matter. So all of the thermodynamic driving forces are selected among properties of this type. So intensive properties is independent of the amount of matter. So what are examples of intensive properties? We have temperature, pressure, density, molar volume, molar enthalpy. So example, in the case of temperature, the total temperature in the system is equal to temperature of that part of the system. So unlike extensive, it's additive. Now we also have what we call state function and path function. So when we say state function, this is a property of a system that depends only on the state or the current state of the system. This describes the system. What are examples of state function? The pressure, volume, temperature, enthalpy, internal energy, also gives free energy and entropy, which will be discussed in the latter part of the course. And when we say state function, this is an exact differential. Example, in the case of internal energy, delta U is equal to the integral of du from initial to final state, or U final minus initial. So take note that for state functions, these are expressed in capital letters. Path functions is the inverse. This is a property of system that depends by which the system achieved a particular state. So examples include work and heat, and they are an inexact differential. So in the case of Q, Q is equal to integral of dq from initial to final path. And take note that in most of the references and PChem books, path functions are written in small letters. When we say first law of thermodynamics, this is associated with internal energy. So what do we mean by internal energy? This refers to the total energy of the system at any given time. This comes from the total kinetic as well as potential energy of molecules which compose the system. And a change in internal energy, since this is an exact differential, delta U is internal energy, final state minus initial state. Since internal energy is associated with the sum of kinetic energy and potential energy, so you know that kinetic energy is energy in motion. So kinetic energy is a formula of 1/2 mv squared, kilogram meter per second squared, or Newton meter, so the SI unit is joule. And potential energy is a stored energy. Now, what are methods of transferring energy in terms of heat and work? So heat is something that an object has. So example, if you have a hot object, so you associated it with a lot of heat. But in thermodynamics, heat is a process here. So a method by which energy is being transferred. So surroundings is also internal energy, which could be transferred to system. So if we will consider the law of conservation of energy, so du, internal energy, is dq plus dw. So du is an exact differential, while dq and dw are inexact differentials. Now, for conventions or changes in internal energy, we have from comparing with initial to final state. If the final is higher, delta U or internal energy increases. If the final internal energy is lower than the initial, delta U or internal energy decreases. Now, if we will be considering the internal energy of the system and surroundings, so if example, heat and work are being transferred, in terms of magnitude, the delta U of system is just the negative delta U of the surroundings. So this conforms to the first law of thermodynamics, that energy cannot be created nor destroyed, but only transformed or transferred. So again, first law of thermodynamics in terms of statement, and that is this one: energy cannot be created nor destroyed, but only transferred or transformed, or the energy of the universe remains constant. Now, what are applications of studying thermodynamics? So one is calculation of energy changes accompanying a physical and chemical change, and determination of maximum or minimum amount of work that can be derived from a process, and to establish relationships among the variables that describes the system at equilibrium. So this is developed around 1850 by Rudolf Clausius, and every system here possesses an internal energy. Now, one basic example here is if an electric motor produces 15 kilojoule of energy each second as mechanical work and lost 2 kilojoules of heat to the surroundings, what is the change in internal energy. So from the first law of thermodynamics, if we will be converting this to equation, delta U is equal to Q plus W. So delta U is negative. Negative here since we lost 2 kilojoules of heat, and since this is work done by the system, negative 15. Negative 15 kilojoule for work. So the total is negative 17 kilojoules. So in the next part of the discussion for lecture 5, we will be discussing the applications, processes of thermodynamics.